Welcome back. In this module, we will investigate the conditions under which a given function will be invertible. Moreover, we will also learn how to find the formula of an inverse function, along with how to sketch their graphs. Here's a very important fact. Inverse functions don't always exist. Consider the simple quadratic function f of x equals x squared, whose parabolic graph is sketched below. Since both 2 and negative 2, or squared, both equal 4, the output y equals 4 can be traced back to two possible inputs, x equals 2 and x equals negative 2. But function outputs must be unique, so would the inverse function of f direct 4 back to 2 or negative 2? This is quite ambiguous, and so we say that f has no inverse function on its natural domain of R, the set of real numbers. If you're able to sketch the graph of a function, you can use what is called the horizontal line test to determine its invertibility. Specifically, a function has an inverse if and only if all horizontal lines intersect its graph at most once. So for instance, it is clear that any horizontal line above the x-axis will intersect our simple quadratic function y equals x squared twice, therefore verifying our earlier conclusion that the function is not invertible. There is a second test for invertibility. Firstly, note that a function is strictly increasing if it is traveling uphill, going from left to right, for its entire domain. Similarly, it is decreasing if it's traveling downhill, going from left to right. A function whose entire domain is strictly increasing or decreasing is called strictly monotonic or injective. This gives rise to what is known as the monotonic or injectivity test, which says that theoretically, a function being invertible is equivalent to saying that it's strictly monotonic. For instance, going back to why our simple quadratic function, y equals x squared, isn't invertible, notice how the function is not strictly monotonic. Indeed, the function is decreasing for negative x values, but increasing for positive ones. However, if we intentionally restrict the domain of this function to, say, only the positive x values, then f will be invertible on that restricted domain. This technique of domain restriction is often utilized on a given function that isn't invertible on its entire domain. Moving on, given an invertible function f, how do we actually find its formula? Well, since f inverse recovers the inputs of f, the first step is to solve for x in the formula for f. Moreover, precisely because f inverse maps the outputs of f back to their respective inputs, if f has domain A and range B, then f inverse will have domain B and range A. Here's an example. Let the function y equals f of x be 3x plus 1. We rearrange the equation for x, giving y subtract 1 or divided by 3. To finish off, we interchange x and y, and so the inverse function is given by the following. Here's another example. Let the function y equals f of x be e to the power of 3x, subtract 2. We rearrange the equation for x, giving the log of y plus 2 all divided by 3. To finish off, we interchange x and y, and so the inverse function is given by the following. Note that since f has domain R and range all real numbers greater than negative 2, f inverse therefore has domain all real numbers greater than negative 2 and range R. Here's another important fact. The graphs of two mutually inverse functions are symmetric about the diagonal line y equals x. You can use this property to help sketch graphs. For example, if you forget how to sketch the log function y equals ln x, but remember how to sketch the exponential function e to the x, well, since they're mutually inverse functions, all you have to do is sketch e to the x and then reflect its graph about the diagonal y equals x to get its inverse, ln x. Alright, here are some practice questions. You should pause the module so that you can attempt these. Here are the answers for the first function. Here are the answers for the second function. Here are the answers for the third function. And finally, here is a summary of what we've learned in this module.